Okay, so now we'll look at the standard reduction potentials. We compare the half reaction that we're discussing to the hydrogen electron, which is randomly, arbitrarily assigned 0, and then we can calculate the cell potentials. Now, there's two things we can do. We can say, I'm going to take these two cells and hook them together, and I'm going to calculate or predict what will happen in nature. And what will happen in nature when you randomly hook them up, the one with the bigger reduction potential will get reduced. The one with the smaller reduction potential will get oxidized. So that's one thing we're going to do, and that's what we're going to do first. The other thing we're going to do later is say, look at this reaction the way it's written. Now I'm going to calculate the standard cell potential for the way it's written, reduction half minus oxidation half, and I'm going to see then, will this be spontaneous? Okay, so you have to read the problem carefully so you know if you're predicting what will happen spontaneously or if you are determining if what is written will happen spontaneously, because they're different.
I just have a question.
Sure.
How do you calculate the standard cell potential for the copper-silver cell? Would it be the...
Are you back a page? What page are you looking on?
Page right before.
Okay, so we look at this. We look at the equation that's going on here, and we look up the two half cells, and we have the larger one is the silver, the 0.80 volts, and the smaller one is the copper, 0.34. And we look at this the way it's written, and we said the silver is getting reduced, and the copper is getting oxidized, and we always calculate reduction minus oxidation. So it's silver minus copper, which is, in this case, the bigger number minus the smaller number.
So do you multiply it by the amount of, like, for example, there are twice as many copper as there are, twice as many silver as there are copper?
Correct. You do not multiply the number in the chart. Okay, we got in the habit of doing that with enthalpies, free energies, and entropies, but we do not do that with these. You just take the number out of the chart as is. No multiplying by coefficients in balanced equations.
What would that final value be? Would it be
0.46 volts. Okay, 0.46 volts. Okay? Okay, so this is a typical problem. Determine the cell potential for a galvanic cell with these two half reactions. Tomorrow what we're going to do in lab is take half cells and then hook them up and see what happens and measure the voltage on a voltmeter. It'll be pretty exciting. So we have the aluminum half. Aluminum plus 3 electrons makes aluminum solid. Copper 2 plus 2 electrons makes copper solid. These are both written as reductions. So the first thing we do is grab our chart and we look up the potentials for them. For the aluminum half, E0 is negative 1.66 volts. And for the copper half, E0 is a positive 0.34 volts. Now we look at these numbers, and if I hook them up, what will spontaneously happen in nature is that the one with the larger reduction potential will be the reduction half. So in this case, it's the copper half. So copper will get reduced. The copper ion will grab 2 electrons and become copper solid. And the E0 for that is positive 0.34 volts. Now, the smaller one will be the oxidation half. So for aluminum, this is going to turn around. So aluminum solid is going to be oxidized to give us aluminum 3 plus 3 electrons. And again, the standard cell potential is negative 1.66 volts. I do not change the sign. I'm turning this around, but I do not change the sign. It's not like Hess's law where we turned an equation around and we change the sign. We keep the cell potential as it is in the chart. Now we add them together, add the two halves together. So I have 2 electrons here and 3 here. In order to add them together, I have to have the same number of electrons in both sides. So I'll multiply this half by 2, and I'll multiply this half by 3. And I do not do anything to those numbers. I don't multiply the numbers, I just multiply the chemistry. And then I add them together and cancel out what appears on both sides, and I get 3 copper 2 plus 6 electrons plus 2 aluminum solid yields 3 copper solid plus 2 aluminum 3 plus 6 electrons. My 6 electrons cancel, nothing else cancels. Now I know the cell chemistry. Now I can calculate the standard cell potential E0. So E0 is equal to the reduction half potential, the larger number, which is the copper, positive 0.34 volts, minus the smaller number, the aluminum, a negative 1.66 volts. So I'm subtracting a negative number, so it becomes positive, and I get my standard cell potential is equal to 2.00 volts. So when you're subtracting this negative number, you're effectively changing the sign. And because the standard cell potential is positive, it is a spontaneous reaction. When we were looking at free energy, we said when delta G is 0, it's at equilibrium. If delta G is negative, it's spontaneous. When delta G is positive, it's not spontaneous. When a standard cell potential is positive, we have a spontaneous reaction, and we have the chemistry taking place in that direction. Okay, now I'd like you to go ahead and work with your groups, write out the spontaneous reaction for these two half cells, and calculate the cell potential.